All right, I feel like we got a more of a computational question here, which will be fun to deal with. The statement reads, refer to problem 7.16, to which the correct answer was some electric field as a position and time. Okay, and what we want to find is find the displacement current density, JD, integrate this to find the displacement current, and then compare ID and I. What's their ratio? If the outer cylinder were, say, 2 millimeters in diameter, how high would the frequency have to be for ID to be 1% of I? All right. This is pretty fun, but let's be careful. One step at a time. So the displacement current density, which we know is JD, is equal to epsilon naught partial of E with respect to T. Well, we just plug in E and take the partial derivative. We see that the partial goes to sine of omega t only. And when we do that, we know that sine goes to cosine, and then we have to tag it with an omega due to the chain rule. And then we can simplify down. We see here that JD is equal to epsilon naught mu naught I naught omega squared over 2 pi ln of A over S and times cosine omega t. But let's recall that back in problem 17 where we had the current flowing down the inside of a pipe and the outside of a pipe with the insulating layer or sheath, that I was equal to I naught cosine omega t. So we can condense this even more, and that's what I highlighted in the purple. So if you're wondering where the cosine went, that's where it is. All right, so for part B, what we have to do is integrate the displacement current to find the displacement current density to find the displacement current. Okay, and again, since we're a cylinder, we're going from radius 0 to A, and then the phi would be going from 0 to 2 pi, since our cross-section is an area, and we have to have a differential area. Let the integral do the work. Most of that's a constant. You see we just get 0 to 2 pi d phi, 0 to A ln A over S, S ds. We'll have to use the rules of logs to split up that A ln of A over S as the ln of A minus S, multiply the S from the differential to both of those, and that's what we see in the next step. Note that the factors of 2 pi cancel conveniently, and then we just take the integral, again, integration by parts on that second part. So that's why we have a plus minus plus in the square brackets. Hope you remember your calculus. And then you see here that the minus sign actually is 2 copies when we evaluate it at A, so they cancel out. And we see that conveniently ID, the displacement current, is equal to epsilon naught mu naught omega squared I times A squared over 4. We see a lot of squared terms here, and we'll see that that is simplified in the next step. So if we want to find the ratio of the displacement current to I, we see that ID divided by I, well, if we plug it all in, we see that the currents cancel, and that's why we substituted it back in part A. And you see that the ratio is equal to epsilon naught mu naught omega squared A squared over 4. All right, but since we want to find a frequency for where ID is equal to 1% of I, or 1 over 100 I, and if we divide by I, then we can see that the ratio needs to equal 1 over 100. Then we can clean up this ratio into a square term, meaning, look, we see that we have epsilon naught mu naught, and we found that that was equal to 1 over C naught earlier in the book, so we plugged that in. We also see that 4 is equal to 2 squared in disguise, so now we have everything written in terms of a square, okay? So you see we have omega squared, A squared, C squared, and 2 squared, and we can formulate that all into omega A over 2C, the whole thing squared. And again, we're looking for where this ratio equals 1 over 100, or 1%. So if we solve this for omega, which is the angular frequency, and recalling that the angular frequency is 2 pi f, or in this text, 2 pi nu, then we see that if we take the square root of both sides of this cleaned up ratio, we get that we want omega A over 2C is equal to 1 over 10. Okay, pretty quick there. And if we solve this for omega, we get 2C over 10A. But again, we were given diameter here. So A, which is a ratio, goes to diameter over 2. And you see here that that's where we get 2C over 5D. The D is for the diameter of the given wire or tube. And if we plug everything in, we see that we have 2 times the speed of light, then 5 times the diameter converted to meters. And we see that we have 6 times 10 to the 10 radians per second If we convert that to linear frequency, that's approximately 10 to the 10 hertz. The thing about this is that this is about 10,000 megahertz. So this is why we don't see these things frequently, or at least why Maxwell didn't see it, because that was way outside of the range at what they were dealing with in radio signals. Pretty cool though.